upper layer to slide anymore. And here it just kind of shows a more natural indication of this décollement that's happening. So I gave you a sort of example of how it would happen in potware. This is how the décollement process actually works in the potware region. So at the top here we have a diagram that shows completely undeformed potware sediments. That would have been before we had the main boundary thrust acting upon this area. And as we look, we can see that as we go on to the next layer, this is a present day cross section. We can see just how much more convoluted the structural geology has become. And at the very bottom of all of this convolution, we can see a purple layer, and that is the salt range layer, which is, if you remember, is the layer with the salt in it that is creating the ductile flow. And so what we're seeing is that due to the bulldozing effect of the main boundary thrust, we have all of this complex convoluted thrust belts and a series of thrust faults. And indeed, in the salt range area, the thrusting is so extreme that the unit has thrust 30 kilometers over itself because the décollement process was so effective. And here's a slightly more naturalized view of the same thing. So now we reach the synthesis portion of the presentation. Well, let's think about what we have. For starters, we have the potware area, which is completely bounded by faults, which is very unique, and seems to be particularly affected by the effects of the main boundary thrust. We know that this was formed by the collision of the Indian Union Plate, and it continues to function off of that today. And we also know that the décollement process is very active in the potware, the faults in the potware are created by the décollement process. As the main boundary thrust acts on the potware plateau, it pushes it and acts upon it far more than other sections along the Himalayan main boundary thrust, and so creates a far more extreme and unique structural geology. So in order to kind of illustrate the synthesis, I came up with something called the Great Paper Towel Experiment. And I have a video of it, and it just kind of illustrates, from my perspective, what I see going on in the potware in a very active way. Sorry, technical difficulties. Where is the video? Alright, seems like it's shut down. Hold on a second, folks. It's coming. Just takes a second. So I want to open this file. Important value of presentations, always have your stuff ready beforehand. Okay, so here it is. Here's the video. I'm going to make it full screen so everybody can see. And I'll rewind it here a little bit. It kind of got ahead of me. So yeah. Before I start the video, I just want to explain some things real quick. So this arrow here represents the main boundary thrust and its effects on the potware plateau. And just FYI, this has been flipped upside down. This would be north, this is south, east and west. And so these perforations illustrate where the salt range layer laterally pinches out. And this central area just represents the potware plateau as it's illustrated. So I'm going to run the video, and I'll let you see what happens. I'm going to let it run again here, and I'll pause it. Alright, so what we're seeing here is that as the main boundary thrust pushes forward on the plateau slides forward far more and far faster than any of the surrounding rocks because it is, essentially lubricated underneath by the salt layer. These areas here represent, on the other side of the perforations, represent the rocks that don't have, as we talked about before, they don't have the décollement process happening, and so they stay in place more than the potware plateau rocks do. And as the potware plateau is pushed forward by the main boundary thrust, the rocks can't deform quickly enough to accommodate the movement of the Potwar Plateau, and so the strike-slip faults on the eastern and western borders of the Potwar are formed. And as we can see, as the main boundary thrust acts on the Potwar Plateau itself, it's pushing it forward so quickly that all the brittle layers duplex up on top of each other into these complex folds. And it is these complex folds that help make the Potwar Plateau so much more valuable, as I will demonstrate in my next slide. Hold on a second, let me get out of the video. Alright. So back to the slideshow. We just said that oh shoot. Get back to where I was. Alright, we are in business. Okay, so now that we've gone through all of these different portions, we can come back to our original question of what makes salt as valuable as gold. And the answer is oil. Because of the complex folding, as I demonstrated with the great paper towel experiment, we get all of these great, essentially, hydrocarbon traps. The thrust and the duplexes are excellent for trapping hydrocarbons, and here we have innumerable versions and portions of the Potwar Plateau that are dedicated to basically just these complex duplexes. There are many Silurian source rocks located beneath the Potwar Plateau, and because of its complex structural geology, it's able to trap the hydrocarbons, whereas other areas along the Himalayan front are not able to do so. So basically, the Potwar declement creates complex hydrocarbon traps, which in turn makes it a very economically valuable area. So our conclusions are the Potwar is defined by the 4 faults that surround it, the 2 strike-slip faults, and the main boundary thrust and the salt range thrust, the structural and stratigraphic influences that created the Potwar were the collision of India with Eurasia and the continued effect of the main boundary thrust on the Potwar Plateau, which is gliding forward on salt faster than the rocks surrounding it can accommodate. The strike-slip faults are formed by this lack of accommodation from the surrounding rocks, so they rupture and create 2 strike-slip faults so that the Potwar Plateau can continue to move forward unhindered. And it all works together to create an amazing oil field that is so very complex and quite excellently structured that it continues to be productive to this day. And so we can conclude, therefore, that the Potwar Plateau will probably continue to be successful, as we can imagine the depth to which it is folded and faulted. And by continued studies of the Potwar region and areas like it, we hope to be able to further our understanding of hydrocarbon trapping and be able to possibly discover new places based off the knowledge that we find. Thank you. And are there any questions?